A very good afternoon to all. Welcome you back for the afternoon session on the FDTP for strength of materials. Sorry. Sorry. So let me introduce our speaker for this session now, Dr. Vadivuchezhian Kaliveeran. So Dr. Vadivuchezhian Kaliveeran is Assistant Professor from Department of Civil Engineering, NIT Surathkal. So he has done his BE in Mechanical Engineering from CEG, and then his ME Aeronautical Engineer from MIT NIST, and a PhD in IIT Madras uh, in Characterization of Friction Coefficient at Contact Interface. So he has been a lecturer in Department of Aeronautical Engineering, Park College of Engineering and Technology, Coimbatore, till 2005, and 2005 to 2009 he has been a research scholar in IIT Madras, and from 2009 he had been assistant professor, Department of Aerospace Engineering in Madras Institute of Technology, NIST, and from 2013 till date he's been the assistant professor at NIT Surathkal. So he has almost 15 plus publications in his name, including the journal and conference proceedings. He has also collaborated with the foreign professors and universities to do his research work. Uh, his he has guided 3 ME projects and BE projects also, and his courses of interest are engineering mechanics, strength of materials, theory of elasticity, uh, contact mechanics, finite element analysis, etc. And he is very well versed in finite element analysis, ANSYS, programming in C. And so, welcome you once again, sir. Thank you so much for taking your time. You may please take over the session now.
Thanks, madam. Thank you very much. Slides are visible.
Yes, sir.
Good afternoon, madam. Good afternoon, faculty members from various colleges. Really, I'm very happy to share my little knowledge with our faculty group. So today, we are going to discuss plane truss analysis. We are going to focus on statically determinate structures. The statically indeterminate itself, it is different section. So we need some fundamentals related to compatibility equations. We have to understand superposition technique, and we have to understand unit load method when we think about statically indeterminate structure. So that's why the organizer they have given specific topics related to statically determinate using method of joint and the method of section. I'm really very happy to share our slides and whatever things we are teaching in our NITK, we are trying to share in front of our group. Madam, slides are moving.
Yes, sir.
Thanks, madam. When you think about truss, where we will see truss member. When we see our cell phone tower, it is arrangement of truss members. When we see power transmission part, it is arrangement of truss members. When we see hanger, all those roof structures, asbestos sheet or any other metallic sheet, it is simply just resting on truss member only. Why do we need truss? Particularly for material saving. When we just use very thick structure for our hanger or for towers, obviously we have to waste more materials. We have to spend money also. One thing you have to remember, when you think about those concrete structure or kind of brick structures or full metallic, thick metallic structures arranged by plates, if there is any failure in those structures, failure may happen due to wind load or any other cyclic load. The failure will happen mainly due to those kind of loads, even sometimes environmental effect. So what will happen? Just what we will do generally, we will eliminate our structure and we will just simply throw. Sometimes we may not use. So whatever materials we have spent on those constructions, it will be totally waste only. When we think about our truss member, there are a group of simple bar elements. Those were arranged in a required form to take care of our application. These members also will experience same kind of loads, payloads, and you also have wind loads, and you also have some additional unwanted forces. So if there is any problem in our structure, sometimes environmental effect also will play main role. Due to that part, what will happen? Our member will lose its strength. Ultimate strength part will be lost. And minor crack initiation will happen if there is any wind effect and if it is subjected to cyclic load. Visually it may not be visible, but there will be cyclic load due to wind effect. A crack initiation and the crack propagation also will happen. Sometimes it will lose strength, sometimes it will lose yield strength. So because of that, what will happen? Material will fail, entire structure will collapse. See, when you think about truss member, only one or two members, they may get problem. They are very close to your loading point, or sometimes they are very close to your severity. Those members may get problem, and we will also come to know that problems are there from our external vibration or some kind of, by observing some unwanted noise. So what we will do, we will just replace those particular members with a new one, or we will try to repair our member, or what we will do, we will try to reinforce our weakened structure with the additional stiffness. In that way, they will repair. So in this particular part, when you think about our truss member, material wastage, it is not happening. If there is any problem, we are trying to replace only that particular member. And the only thing we need maintenance, proper painting, and we need proper oxidation effect part also we have to take care. Using sacrificial anode, sometimes when you use steel or other kind of. So in this case, when we say truss is something like group of bar elements subjected to, like kind of arranged in a particular way. When we say bar, bar is subjected to either compression or tension. In this particular problem, we are planning to keep all those members in a plane only. Please remember, in this particular problem, we are planning to keep all those members in a plane. We know our plane, X, Y plane, Y, Z plane, Z, X plane. We can follow any one of those planes and we will keep those planes and we will keep all those members in a particular plane according to our requirement. And we are trying to solve. Only one important thing, members, each member will be subjected to either compression or tension. So now how those members are connected? You have one flange plate. In that one, we are connecting our members by frictionless pins. It is main assumption. Obviously, friction will be involved when you keep any contact. When you keep any riveted joint or any other part, obviously friction will be involved. So it's also interesting one. When we just introduce friction part, our problem is very highly complicated. Friction itself is a different domain. Many failures will happen in those joints only because of that threading effect. If they are subjected to cyclic load, obviously in that contact interface we will have threading effect. So many failures will happen in those joints only. So when we see our truss members, truss part, in our practical application, bridges, railway bridge, comfortably we can analyze our railway bridge using 2D plane analysis. Similarly, roof structure also. Roof structure, we can just consider one kind of plane and we can analyze. Sometime we will have some kind of loading mechanisms with the truss part. Some load transfer mechanisms also we need. So we may need little supporting subsystem. That system, it is just like arranged by various members, truss members. Now, when we see our truss, this is our truss, entire thing is noted as truss. Each one is truss member. Those members are connected by points, or joints, or nodes. So, first assumption, those joints we have to understand. Members are connected by frictionless pins. In this one, we are not bothering about our flange plate design. When I show this analysis, I am not trying to show anything related to your flange plate design, and we are not trying to study anything related to contact related problem. Directly, we are trying to consider only that whole structure and we will see all those nodes or joints. Second assumption. When you think about our second assumption, you may have variable loads. Your member will experience variable loads, mainly from our wind effect. Or sometimes you may have some kind of payload effect, something like supporting structure. So we are not just like keeping our distributed one on those members. We are not trying to analyze with that mode. What we are trying to do, we are trying to find our resultant and we are trying to fix our resultant where it is possible. That resultant we are trying to just place at those nodes. We are trying to maintain that resultant part and we are trying to just like maintain equilibrium from our simple moment theorem. we are directly comparing. Varignon's theorem. So we are trying to ensure our resultant in a particular line, and we are placing our nodes. In that way only we are trying to show. So first assumption, there is no friction. Second assumption, we are trying to place our resultant and we are trying to distribute properly our resultant part into joints. It is very important thing. We cannot randomly placing our applied loads. But in our practical problems or some other examples, directly we are taking only P1, P2, P3 instead of just showing those distributions. And we already said it is like group of bars only. So we can comfortably just consider only compression tension. So when you think about your compression tension, obviously the axial stiffness part we have to consider. And the axial displacement, it is like cos. What is our corresponding effect? That is displacement only. When we apply load, obviously it will be extended or contracted. So those portions are involving for our compatibility part when you just think about your statically indeterminate structure. And when you think about a member lateral deflection, here we are trying to avoid. We are trying to consider only bars. We are not trying to consider anything related to bending effect or transverse effect. Even twisting part also we are trying to avoid. A general category we will just say 3 degrees of freedom per node. Like we are 6 degrees of freedom per node, U1, V1, W1. And we can also say theta 1, theta 2, theta 3. Per node we can consider. 6 degrees of freedom we can consider for general arrangement. A plane truss, in this case we are trying to just fix only loads. And the displacements U1, V1. In that way only we can consider. So now we have to note this. Our self weight of our member. So each member will have self weight. Self weight part will be ignored. You have to remember, self weight part, it is totally ignored. Self weight will play main role. Self weight, it will play main role, and it will also just give enough information. But when you consider a self weight, obviously we have to consider our transverse effect. So that will cause problem in our analysis. To avoid unnecessary complications, we are trying to remove our transverse effect. And we are trying to just think only rigid. When you think about our plane truss analysis, for statically indeterminate case, member is rigid. And we are not bothering about anything related to axial displacement. And one more thing we have to note, members, they are not subjected to stable related issues, something like stability, buckling effect. They are not buckled. But the actual situation, we are facing problem, transverse effects, stability related issues we are trying to see. But one thing you have to note, in this particular analysis, plane truss analysis, we are avoiding bending effect and buckling effect. When I say buckling, obviously it is related to stability related part. Next you have to note, what about our supports? Where we are placed? Please note, our supports are placed only in those joints. If you have any load, you have to place those loads in those joints only. Similarly, any support, if you see, those supports should be placed in those joints only. You have to remember. So when you just think about your plane truss analysis, we can consider these main assumptions. when you are considering plane truss analysis, you are not bothering about your direction cosines. Directly you can use your scalar approach and you can identify your components, force components, and you can solve your problem. When we think about your three-dimensional space stress, like space stress, you have to think about your direction cosines. You have to think about your vector pattern. Unit vector, you have to understand. Direction cosines, you have to understand. And you should understand your all position vector or all those concepts we have to thoroughly you have to understand. Now, we have to sense our joint and members. When I say one joint, in that joint, minimum we need two members. When we say joint, minimum we need two members. Then only it is proper, it is truss. So each joint needs minimum two members to connect. In our problem, what we are trying to do, we are trying to just consider outward forces. We are just assuming all those members are subjected to outward force. And what is our main aim of our problem? That part also we have to understand. When you think about your main objective, it is mainly related to force part. We are trying to understand our force, internal member force. When we know our member force, you please remember, from our member force we can identify what is our corresponding stress involved in a member. So we can compare our stress with the available ultimate strength or yield strength part according to your design criteria, and we can fix our problem. So where we are starting? We are starting from force. And beginning part, we are not worrying about our elastic effect. We are not thinking about our deformation. We are not thinking about our axial displacement. We are trying to fix only force. We are trying to just treat our entire system as rigid, and we are trying to understand our internal reactions. So now we have noted each joint we have very simple member, two members are connected. Each joint minimum we need two members. So now we are also just starting with this outward force only. With that assumption we are starting. Later we will correct after seeing our negative side. We can say it is under compression. When we see positive, it is under tension. Now we are going to see how it is positive, how it is tension. When I show outward force, how it is noted as tension. For that one, I want to just to show one simple bar element. This bar element is subjected to tension. Similarly, we are also taking one more bar element. It is subjected to compression. So when I show free body diagram of this tensile member, it will be like this. You have your applied load. When I just isolate this support from this main structure, you have your support reaction. Now you have to remember this. When I split this L into three segments, L1, L2, L3, we can see our internal equilibrium, and we are trying to see static equilibrium of this part. We know our boundary condition in this problem from load point of view. It is like known load in this plane. So that's why we are directly keeping this. When I cut this portion, we have our internal reaction, that is P, to maintain our axial force equilibrium. Similarly, the mid element, this is our mid element L2, that will be also experiencing P and P. You please remember to balance this, it should be towards outward. Here also it should be towards outward. So next, our remaining one, which is this portion is attached to our fixture, and the other one, your isolated part of your mid portion. So that will be also experiencing P, and this will be also experiencing P. When you are thinking about this portion, you have to remember all those segments, they are subjected to tension. So now, when you think about your compression, you please note same situation we are trying to see, only loading direction is changed. Three segments L1, L2, L3 we are considering. We are starting from this known condition. This is our known condition from load point of view. We are trying to use, we are not changing the direction because direction is given in this problem. After that, to maintain our balance, the kind of static equilibrium in that L3 portion, it should be towards inward. To maintain our equilibrium, obviously, that mid portion, it should be towards inward only, here also towards inward. In this last portion, like, topmost one, that L1 portion, you have P and P. In that support, in that fixed support, you have P only. You have to remember, you have L1, you have L2, you have L3. When we are thinking about two different modes, tension and compression, in the tension part, you have your plane. In that plane, all those forces are outward only. So when you see outward force with the positive magnitude, end of your calculation, if you see positive magnitude, so whatever sign you are considering in a particular member, that is subjected to tension. Member is subjected to tension. Member is under tension. When we see negative sign, that indicates you have to change your sign. When you change our sign, obviously it will be in that mode only, towards inward. So that part says our compression. You have to know. So these things are very, very important to take care of our tension compression portion. Because in this Truss analysis, we are trying to identify member forces only. From our member force, we are trying to fix our stress. But stress part, it is very, very important. We have to understand our tensile strength and we have to understand our compressive strength also. For different materials, we have tensile strength is different tensile strength. And for compressive strength also, it is totally different. They are not same. Their behavior part is totally different. So that's why that sign part we should not miss. Some members, they are weak in tension. Some members, they are weak in compression. You have to think about the material. Sometimes you are using different materials. So that material part will play. That's why when you are thinking about your truss analysis, generally people, they don't simply leave, they will think about sign also. Sign is very, very important along with your magnitude of your member force. Next level, I'm trying to show, you have your truss. In this truss part, how we are going to arrive our m equal to 2j minus 3. So this is very important thing. Many of our books we read and we are trying to understand how they are maintaining this m equal to 2j minus 3. For our understanding part, what we are trying to do, we are trying to consider group of members and those members arranged in a particular fashion. So now it is something like square, we have one diagonal. There are 5 members in this problem. 4 joints are involved. And you have joint 1 and joint 2. In the joint 1 and joint 2, you have your supports. Joint 1, you have pinned support. In the joint 2, you have your roller support. You have to remember, we already discussed, each joint, we need minimum 2 members. Then only it is possible. We can just like connect our members. Each joint we need minimum 2 members. After that we can add any number of members. That is our wish according to our strengthening part. But minimum we have to start from 2 members. So each joint minimum we need 2 members. When you are thinking about this case, this joint, each joint minimum we need 2 members. So now we can have one kind of relation 2j. This j is multiplied by 2. This 2 says each joint needs minimum 2 members. And what is this 3? 3 says your number of support reactions. In this problem, it is statically determinate from external point of view. When I consider this whole structure, I am just seeing only external supports point of view. From external supports point of view, this is statically determinate. And those supports, you can see one is pinned support, another one is roller support. So you can comfortably, you can note, it is statically determinate from external support point of view only. Internal we will see later. So this 3 says our reactions. Support reaction, available support reactions. Sometimes when I use, here also pinned. At joint number 1 it is pinned. Joint number 2 also pinned. This 3 should be 4 now. Why? Because pinned support, it will resist both vertical and horizontal reactions. Similarly, when you think about your joint 2, when I use pinned support instead of roller support, obviously that will be also experiencing both horizontal and vertical reactions. So when you think about this 3 part, now this 3 should be replaced with the 4 one. Please note. So now this 3, it is for statically determinate from external supports point of view. I am trying to write. So don't please simply remember, always it should be 3. It may be 4 also. Okay. So when I show 3, it is something like statically determinate from external supports point of view. You have to remember. Now, when I just merge them, 2j minus 3, I am getting corresponding members involved in this problem. So now number of members 5. See, 4 joints, 2 into 4, 8, 8 minus 3, 5. So we have 5 members. By observing many set of trusses, and they are trying to identify. It is finally just like based on our observation, we are fixing our m equal to 2j minus 3. See, one thing you have to remember, in this problem, we have our nodal load or applied load at this joint number 3. You have to note, at 1 we have pinned support, at 2 we have roller support. So 1 load and 2 supports. Load is simply saying non-essential boundary condition, and this pinned and roller supports, they are directly representing our essential boundary conditions. You have to note this. So next level, we have to understand how this part is coming. See, m equal to 2j minus 3, this j is multiplied by 2, because minimum we need 2 members. And 3, it is support reactions. So when you just measure them, obviously we will be getting our corresponding numbers. Based on this, it is only observation. From various models, we are trying to just observe. Finally, we are just arriving this set of equation in the form of member and joint and support reaction. See, now you have to note this part also. It is very important. M equal to 2j minus 3. When we see, it is perfect truss. When m greater than 2j minus 3, it is redundant truss. When m less than 2j minus 3, deficient truss. See, when I see this problem, only we can, through this problem only, we can understand what is perfect truss. M equal to 5, j equal to 4. We already noted. Now we are trying to substitute whether it is possible. Yeah, it is possible. M equal to 2j minus 3 only. Now in this case, it is 5 equal to 5. One thing you have to note, from external point of view, it is satisfying, statically determinate. At the same time, it is also perfect truss. When I say perfect truss, please remember internally also it is satisfying, statically determinate. What is perfect truss? When I say perfect truss, internally also it is satisfying, statically determinate. Next level, I want to see your other one, that redundant truss. The redundant truss, you have to note how many members you have. You have 6 members. Number of joints, you have 4. Now you can see m is greater than 2j minus 3. Please note, in this case, I am not disturbing your external supports. From external supports point of view, still we are maintaining statically indeterminate. If I go for statically indeterminate, obviously that external support will be little disturbed. Here we can place one pin support. Here I'm retaining only one roller and one pin. So that's why 3 part is 3. We are writing this 3. But when you substitute our joint information, that is 4, and you have your reaction 3. So 2j minus 3, it is 5. So 6 is greater than 5. You have to remember. In this particular problem, we have more number of members. It is for our some other requirement. Sometimes it may be used for our some other strengthening part. Why do you need additional member? Because we have to strengthen our member. Entire truss, we want to just go for additional structural stiffening part. That is fine. But what is your statically indeterminate when you think about our internal portion? When I say internally, it is not statically determinate, it is statically indeterminate. Please note, when we just solve our problem, in this case, it is possible. Directly we can solve. We don't want any compatibility equation. But when I want to just solve our internal reactions or internal member forces for this redundant truss, we have to use our compatibility equation. You have to remember this. So from external supports point of view, it is statically determinate, but from this internal members arrangement, when you think about your internal members point of view, it is not fine. You have to just think about our compatibility equations. Next, we have to note this deficient test. When you're thinking about this part, for your understanding portion only, I'm trying to show. M equal to 4, now J equal to 4, 2J minus 3. Please remember, M is less than 2J minus 3. 2J minus 3 it is 5, but available members 4. When you think about this part, it is deficient truss. It is not sufficient to take care of your required load or some kind of application. We have to think about one additional member to take care of our stiffening part. When you keep more number of members, obviously stiffening will be taken care. But sometimes unnecessarily we should not add, because those members may not take load. Those members are noted as dummy members. We will see all those things in our problems. So now, how we will solve those problems? When you think about your plain truss analysis, there are 2 different approaches: method of joints, method of sections. When you say method of joints, you are trying to use your concurrent category. You are trying to fix one particular joint, and you are trying to see your applied loads and your internal reactions, and you are trying to solve your problem from your force equilibrium point of view. So now you have to note this. In the statically indeterminate structure, Here I want just to show, instead of using 3, we are trying to R is 4, because you have one more pinned support. It is statically indeterminate from the external supports point of view, but internally it is fine. You have to know. So when you find both situations, like statically indeterminate from internal support reaction, internal compatibility equation, in addition to your equilibrium equations, you have to remember. So we said there are two methods to solve your problem. First one is method of joints, another one method of sections. So we will consider method of joints. In that method of joints, what we are trying to do, we are trying to consider various joints. We are trying to name our joints A, B, C, D. And we are trying to name our members AD member, AB member, BC member, CD member. When I show method of joints, we are trying to use only concurrent system. Please note, we are not worrying about anything related to moment vector. Just concurrent. When we use concurrent, force equilibrium along x direction, force equilibrium along y direction, both are equal to 0. Static equilibrium. So each joint we are trying to fix our concurrent category, and we are trying to solve our algebraic equations, and we are trying to identify our member forces. First we will see statically determinate or not. When I see these two supports, it is obviously statically determinate. Why statically determinate? From external point of view, we have two unknown reactions. One is horizontal reaction, another one is vertical reaction. In this case, we have vertical reaction. So there are three unknown reactions in this problem. We have force equilibrium along x direction equal to 0. Through that way, we can eliminate this horizontal reaction. Force equilibrium along vertical direction, we can keep one more equation, that is V1 plus V2 equal to our applied load. And we will also fix moment equilibrium with respect to this A to take care of our support reactions, not joints. So now it is possible for you to fix your number of unknown reactions in this problem. Now after that, we are trying to check whether it is statically determinate or statically indeterminate from internal members point of view. So that's why what we are trying to do, we are trying to fix our number of members, number of joints, and m equal to 2j minus 3. Formula we have noted for perfect truss. So when you substitute our number of joints, obviously we are getting phi equal to 5. So this is perfect truss. In this problem, you have to remember it is satisfying both internally and externally from statically determinate point of view. So this problem is statically determinate from both internal members point of view, at the same time from external supports point of view. So we are trying to show how we are going to fix our support reactions. This is our relevant free body diagram of this truss. For our understanding purpose, I want to just to show only one simple truss. So it can be whatever methods I am trying to just to show, it can be extended for any number of members with any complicated shapes. Say here you have three reactions we have noted. So three equilibrium equations we can use. One is force equilibrium along x direction, force equilibrium along y direction, and we can consider our moment equilibrium equation. Moment equilibrium equation we can consider either at point A or point B or point C or point D. We can consider and we can solve our problem. So when you just fix our force equilibrium along this x direction, fortunately we don't have any inclined applied loads, so that's why HA equal to 0. And we have only vertical equilibrium, VA plus VC, that is just like subjected to equal part, that is applied load. And we are fixing our moment equilibrium. In this case, we are trying to keep our XY like this. y is upward, x is towards our right hand side direction. So x to y counterclockwise direction. So when I see counterclockwise, obviously that is noted as positive sign. Clockwise is negative sign. So now we are trying to fix our moment equilibrium with respect to point here. So Vc into 3, it produces counterclockwise moment. P into 1.5, it produces clockwise moment. From this, we are arriving our Vc equal to 5 kN. After fixing this part, Va and Vc portions are known. When Vc is known, obviously, we are trying to substitute this one in this equation. We are arriving our Va. So Va, Vc, now we have noted those support reactions are very important for our calculation, number force calculation. After fixing this, we are trying to check our joints. Joints A, you have joint A, joint B, joint C. There are 4 joints. Where we will start our first step solution or starting point. Which joint should be considered as starting joint to take care of our steps? When I start from this joint number B, joint B, there are 3 members. Please note, this joint B is connected by 3 members. According to this plane truss analysis, we are trying to use only concurrent. It is concurrent when I see plethora of joints. So in this plane truss analysis, you have to note force equilibrium along X and force equilibrium along Y. But available unknowns in this problem with respect to joint B, there are 3 unknown member forces. So we should not start from joint B. You have to remember. Similarly, when we are thinking about our joint D, in this situation also we have 3 unknown member forces, but available force equilibrium equations, they are only 2: force equilibrium along X and force equilibrium along Y equal to 0. Force equilibrium along X equal to 0 and force equilibrium along Y equal to 0. There are 2 force equilibrium equations, but available member forces with respect to this joint D, we have 3. So now you have to note, we cannot start this point D as a starting point. Similarly, we cannot start this point B as a starting point. So now which is feasible? Which can be treated as a starting point? Either we can start from joint A or joint C. When you think about your joint A, already we identified support reactions. Only we have 2 unknown member forces at this joint. At these joints, we have only 2 member forces. Joint A, joint B, we are finding only 2 member forces. So when you use our force equilibrium along X equal to 0, force equilibrium along Y equal to 0, we can identify our member forces. So it is very important thing we should not forget. So that's why our starting point, it is from A. Now, when we consider our A, there are 2 member forces. That's why FAB, FAD. FAB, it is F1. FAD, it is F4. We are writing like this. The 1, 2, 3, 4, 5. In that way, it is just written. That's why F1, F4. It is noted. Now, you have to note this angular orientation. It is very, very clear. 3 meters, 3 meters, 3 meters. So obviously it is 60. This is also 60. This is also 60. Sometimes angular orientation is also tricky. You have to think about that. Now, in addition to these member forces, these 2 member forces, we also have one support reaction, external support reaction, that is VA. That VA should be included. If you find any support reaction, please note, you should not simply leave. You have to retain. Any applied load or support reaction, you have to use. So now, With respect to this joint A, we are trying to identify our member forces F1, F4. Please note, we already said we are trying to use only all those member forces. They are subjected to external output, something like outward normal one. So when I say outward normal, obviously they are under tension. But we have to verify those sign part. We are just assuming in this way. All those members, they are just subjected to that outward force. That's why F1 towards outward, F4 towards upward. So now we are trying to use our force equilibrium along this x direction equal to 0. So now F1 equal to F1 plus F4 cos 60 equal to 0. See, just we are trying to project this F4 along this axis. We are getting our component F4 cos 60. So now force equilibrium along this horizontal way. In this horizontal way, we have F1 and we also have F4. When you just like project this F4 along this x-axis, we are getting F4 cos 60. Please note. So now we have F1 0.5 F4 equal to 0. You have to note this. This is very, very important thing. One more thing you have to note, force equilibrium along this y direction. In this y direction we have VA and I am trying to project this F4 along this y direction, F4 cos 30 or F4 sin 60 also fine. Cos 90 minus theta, that's why it is sin 60. So VA is towards positive y direction. F4 when I project F4 cos 30, it is towards positive direction. Now we are getting F4. Please note our F4 magnitude of our member force along this fourth member or AD member, it is just like attached with a negative sign. This indicates that our member AD, it is subjected to compressive force. So now we have to note our other one, substitution part. We identified F4. Now this F4 should be substituted in this equation number 2 and we are trying to take care of our F1 part. Please remember, when we substitute, we are getting 2.887 kilonewton. It is attached with a positive sign. So what it indicates? Your member AB or member 1, it is subjected to tension that is coinciding with this positive sign. So we no need to bother. We can comfortably say our member AB or member 1 is subjected to tension. Magnitude of your tensile force along this member AB, it is 2.887 kilonewton. But when you think about your member AD or member 4, it is subjected to compressive load only. We are starting with the tensile part, that is our assumption. But when we see our equilibrium equation, after solving our equilibrium equation, our F4 or FAD, it is attached with a negative sign. So now we conclude that this member is under compression. So please note, after fixing this member force, like when you see our member forces, when you see these member forces, we can obviously arrive our stress involved in those members. When you see your stress, things are very simple. You can identify our strength related part. So next we have to identify other joint. After fixing this joint A, now we identify two member forces. Next we have to think about our joint D. In the joint D, we have three unknown member forces. We already arrived our F4. Only we have to note F5 and F3. When you think about this D, joint D, please note our joint D is subjected to externally applied load. That is P equal to 10 kilonewton. We should approve, we have to incorporate that applied load also when you are solving our problem. You have to incorporate both load, member forces. Similarly, you have to incorporate your support reactions and member forces for your analysis. So in this case, in our previous joint A, we have incorporated our vertical reaction. But when you think about this joint D, there is no support reaction, but we have our applied load in addition to those member forces. So now you have to note joint D, we have our applied load that is 10 kilonewton, and you have to note this. There are three member forces, F4, F5, F3. You have to remember the total angle involved, an angular orientation that is 60 degree. So this portion is 30, that portion is 30. So now we can identify this portion is F4, and we have already given this is our member 3 and this is our member 5. Now we can just say F5, F3. So we are getting our F5, F3 using our force equilibrium equation. Force equilibrium along this x direction equal to 0. We are trying to keep our axis orientation like this. In the previous case, XA, YA was fixed at joint A. Now XD, YD is fixed at joint D. When you are thinking about this part, minus F4 cos 60. Please note, we have remaining angular orientation 60. Just we are trying to project. It is mainly applied from our dot product, you know. So F4 cos 60, now it is towards our negative direction. Similarly, when I just project this F3 along this XD direction, we are getting F3 cos 60. It is coinciding with our positive direction. So now you have to note minus 5.774 into 0.5 plus 0.5 F3. So when you just fix this thing, we are getting our F3 equal to minus 5.774 kilonewton. Similarly, we are also trying to see force equilibrium along this y direction. In this y direction part, I can simply project F4 along this vertical direction, F4 cos 30 or F4 sin 60. It is towards our negative direction. F3 cos 30 or F3 sin 60, it is towards our negative direction. And we also have our F5. Please note, F5, it is towards our downward direction. This portion you have to note. Similarly, this 10th one, this is our at joint number D, we have our applied load that is 10 kilonewton. It is towards our negative YD direction. So that's why minus 10. So now, in addition to applied load, three member forces, we are trying to just keep in this form. Minus 10, minus F5, and we have other components. So now you have to note this, F5 we got, that is 0. F3 we got, that is attached with the minus 5.774 kilonewton. After seeing this thing, we can understand this member, it is subjected to compression only, and this middle member BD or member 5, it is just experiencing only 0 load. So this member is noted as dummy member. You have to note member which is taking 0 load, member which is experiencing 0 force, 0 internal force, that is noted as dummy member. When you see this problem, when I just remove this member, these three members are sufficient to take care of our problem. Still, our perfect truss situation will be existing. You can understand. So simply we are just adding this thing. That's why it is not contributing any force carrying part. So now you have to remember other joint we have to understand. So joint A we have noted. Joint D we have noted, we identified member forces. Next, joint B, please note, when you think about our joint B, there are again three members, FBA, FBC, FBD. So that's why we are writing like this, FBD, that is F5, it is F1, it is F2. We are starting with all that outward normal only. We are trying to keep our local coordinate. Please note, all those joints, we are trying to use local coordinate. The first joint A, we are keeping XA, YA. The second joint D, we are trying to keep like this, x d y d. The third joint B, we are trying to keep our axis x b y b. Now you have to remember this. Force equilibrium along this x direction equal to 0. Force equilibrium along y direction equal to 0. Because it's a plane truss problem, we have obviously two coordinates. So we can use our force equilibrium along x equal to 0 and force equilibrium along y equal to 0. We already arrived our F1, we already arrived our F5, only F2 is missing. So through this way we can identify force equilibrium along this x direction equal to 0. From this we are getting minus F1 plus F2. You know our F1, so now F2 part it is 2.887 kilonewton. See, like after fixing this thing, you have arrived our F2. From this joint also we can get our F5. Force equilibrium along this y direction, F5, we are trying to keep member force along this fifth direction or fifth member plus 0. There is no load, applied load, and it is equal to 0. So in this way we are trying to fix our F5, F5 equal to 0 kilonewton. After fixing our member forces, now we have arrived member force along 4, 1, 5, 2 and 3. We should not leave as it is. We have to make one tabular column so that it will be easy for us to remember which one is under compression, which one is under tension, and we can also proceed our further steps related to design. So now you have to note this, our AD, AB, DB, BC, DC, BC, we are getting minus 5.774 kilonewton, it is under compressive nature, and AB it is 2.887 kilonewton, it is under tensile nature. DB it is 0 kilonewton, that is dummy member, and DC we have to note it is minus 5.774 kilonewton, compressive nature, and BC it is 2.887 kilonewton, it is under tensile nature. So by directly seeing our plus minus, we can say compressive tensile. You please note in this problem, it is very simple problem. When you understand this problem, you can solve any number of problems under method of joints. So we, instead of just taking one big problem, we can take one simple problem. When you consider one very simple problem, it is easily we can identify, and easily we can just like check our hand calculations. That's why I took this problem. And we have identified these member forces. I want to just convey one important message in this problem. After seeing our support reactions, there is no HEA. We have only VA, VC. So after removing this part, HEA part, we have VA equal to 5 kilonewton, VC equal to 5 kilonewton. See, now you have to remember this important point. You no need to just like proceed your other steps. Calculation of this part is not needed. Calculation of this part also not needed. Why? It is symmetry with respect to vertical plane. Whatever member force you have arrived along this AD, it should be same for this BC with magnitude and sign point of view. Whatever force you are arriving from this AB, it should be same as your BC. You have to remember. So when you are thinking about your mid portion, with respect to this mid plane, it is maintaining symmetry. Now you have to remember, when do you say symmetry? When you will consider symmetry nature, you have to remember, when you think about your symmetry part, it is very, very important thing you have to remember. 3 constraints should be followed. First one, your structure should be symmetry. When I see this truss member, it is symmetry with respect to this vertical plane. That's why your structure should be symmetry. Geometrical point of view, it should satisfy. That's why structure should be symmetry. Second one, loading point of view, it should be symmetry. When I cut this portion with respect to this plane, I will get 5 kilonewton this side, Similarly, in the right hand side, I will be getting 5 kilonewton. You have to remember. Next level, you should also note, we have to think about our support reactions. After fixing our support reactions, now we have eliminated this HA. Now we have only vertical reaction. This VA is taking only 5 kilonewton, VC is taking only 5 kilonewton. So now from support reaction point of view, we are seeing symmetry only. So 3 constraints you have to maintain when you think about our symmetry situation. First one, loading point of view. Second one, support conditions point of view. Third one, structures point of view. When you satisfy those 3 constraints, if those are matching your symmetry, obviously that particular structure is symmetry. Then only you can say symmetry. Sometimes your structure may be symmetry, but loading may not be symmetry. Sometimes loading structure will be symmetry, they will maintain symmetry nature, but your support conditions, they may not be symmetry. So that's why you have to, when you think about your symmetry, some situation, sometimes you have many number of members. So for that particular situation, instead of solving all those number of members, you can just introduce symmetry concept and you can just solve either left hand off or right hand off. In that way, we can fix our problems. So member force calculation, it is very, very important for our truss analysis. Now, I will show one simple example. You have your truss. This truss, it is like cantilever type truss. And you have many members. In the topmost location, you have pinned joint. And this location F, you have roller joint. You have to understand how we are trying to identify our member forces. When you understand our previous problem, that this problem is very, very simple. Now, what I am trying to do, when you see your cantilever type truss, you no need to go for your support reaction calculation. Why? In the joint A itself, you have 2 members. We can start from this joint A, we can solve our problem. Why we are unnecessarily worrying? So that's why joint A we are trying to start and we are trying to fix our problem. You know, free body diagram, this whole truss should be HG, VG, HF. And you have your applied load 100 Newton. We are trying to name our various members. See, like kind of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 members. How many joints you have? 1, 2, 3, 4, 5, 6, 7. 7 joints we have. You have to understand M equal to 2j minus 3. See, this portion is very, very important. J equal to now 7. So 2 into J, 2 into 7, 14. 14 minus 3, 11. How many members we have? 11. So now please remember, this is perfect truss. When I say perfect truss, it satisfies our internal part. Internally, it is statically determinate. We don't have any problem. Now we have to check our external supports. The external supports also, we have 1 pinned support and 1 roller support. Obviously, it is also satisfying our statically determinate. So from both external and internal point of view, now this truss, this whole truss, it is statically determinate. You have to remember. And when you just solve your truss problem in your practical situation, you should always understand your dimensions. In this problem, why should I take? I want just to show something about dimensions, how you are going to handle. And you are trying to just to show your applied load where it is active, and you are trying to just to show your dimensions, how you are going to handle. So when you think about your whole truss, you have 3, your bottom length is, total bottom length is 3, vertical length 1. So now what we can do, we can just identify what is our corresponding angular orientation. So tan alpha, which is equal to Fg by AF. GF by FA, yeah.
alpha, it is 18.417. Now, after fixing this thing, what we can do, we can identify our corresponding this portion, inclined length, we can identify. We know this length and we know this base length, so we can identify this inclined length. Similarly, we can also identify width of our ED and CB. See, ED and CB, these portions you have to note. How we are trying to do? We have our similar triangle principle. For this whole truss, it will be like this. For the smaller one, see, we have one small triangle. But both the triangles, we have same slope, no? The theta, alpha part is same. Alpha part is not changing. So what we can do? We can get this length. So that's why 1/3, which is equal to x by 2. According to this bigger triangle, this vertical part is 1 meter. Here x, for the smaller one, it is x. Next, what is our base length? It is 3 for this whole triangle. But for this small triangle, it is 2. That's why 1/3 equal to x by 2. Using that thing, we are identifying what is our ED. Next, what we should do, we are trying to understand about CB portion also. So in that CB portion, we have one small triangle. In the smallest triangle part, what we are trying to do? We are trying to fix our base length comparison. Here also slope is same. That's why we are using similar triangle principle. 1/3, which is equal to y by 2. That y is 0.33. X and y, those are not axes. Just like we are trying to give our magnitude representation. After fixing these heights, ED and CB, we can just think about our calculation. So now this portion is known, this portion is known. Now this angle also known. Now this angle, 1 meter, 1 meter. So now obviously you know what is this. This is 45 degree and this one also 45 degree. We can solve our problem. See this whole angle, it is just like 18. We have noted. Now you have to note this. This is 90, 18. Approximately this is something like 18.417. Now this angle we have noted. And this angle also we have noted 45. So the remaining angle we can understand. And similarly, we can also note this length. This length is known. This length is known. We can use our sine rule. We can identify other member lengths and the angle, corresponding angle. So we are doing same thing for our member length calculation. Either we can use sine rule or cosine rule. That is possible. And we are trying to fix our all those members. First, dimension part is very, very important. After fixing our dimension, what we can do, we can just follow our support reaction calculation. In this problem, support reactions are not needed actually. Directly we can start from this point here. But to maintain our general procedure, we are trying to show for your convenience, we are trying to just give all those general details. See force equilibrium along this x direction. When I show HF, it is acting towards our positive x direction, and this Hg also available. So Hg equal to minus Hf, and we are trying to fix our force equilibrium along this y direction. So Vg and our applied load under both are in the negative y direction. Negative y direction. That's why Vg equal to minus 100 Newton, and we are trying to fix our moment about point F. So 100 into 3, it produces clockwise moment, and you have to note this Hg, it will also produce moment about this point F. So Hg into 1, it produces clockwise moment. According to our xy, counterclockwise moment is positive, clockwise moment is negative. That's why we are trying to keep negative sign at these locations. After fixing this thing, we are trying to fix our Hg part, and Hg equal to minus Hf. So Hf equal to 300 Newton. Now it is very, very cool portion. Now Hg, Hf portions are known, Vg also known. We have identified these things. We can start our starting point. Either this F, because Hf is known now, or point here. Remaining locations, it is not possible. We cannot start directly. We need only minimum 2 member forces, either this location or this location. So these locations are super comfortably we can solve our problem. So we have to identify something like starting point is important in our all those problems. So now we are trying to fix our joint A. In that joint A, there are 2 member forces. So FAC, that is noted as F1 according to our notation, F1 and F2. And in addition to those member forces, we also have our applied load, that is under Newton. That portion is shown. So with respect to this joint A, we are trying to fix our force equilibrium along this x direction equal to 0, force equilibrium along y direction equal to 0. We are trying to arrive our equations in this way. When you think about our force equilibrium along x equal to 0, you have to remember F2, it is towards negative x direction. We are trying to use our local coordinate only. This is XA, YA. So when I consider summation of Fxa equals 0, it is minus F2 minus F1 cos 18.417. And other thing, it won't be contributing towards XA direction. So from this, we are rewriting this equation minus F2, which is equal to 0.949 F1. Next, we are trying to see our force equilibrium along this y direction. Under Newton, it is towards negative YA direction. So F1 cos 90 minus 18.417, that is sine 18.417. And we have 0.316 F1 equal to 100. So F1 part is now 316456. After fixing this F1, it can be substituted in this equation number 2. Now F2 equal to minus 303.17 Newton. I want to just to convey one important message. F1, it is attached with a positive sign. F2, it is attached with negative sign. So these information will just directly say member force, that member F1, it is subjected to tension. Member F2, it is subjected to compression. So directly we can note. Next level, we can just start this joint C. In the joint C, you have to remember it is connecting 3 members. Member 4, member 1, member 3. Member 1 we already identified from our previous calculation. So only 2 member forces are connected, F4 and F3. But one thing you have to remember, AC, CE, PG, they are in the same line. So whatever member force it is experiencing, same will be existing in that other 4 also. F4, we will see 316456. So in this case, F1 also 316456. Because the same line, same member force only should be existing. So like in this way, the C part we have noted. Now C, we have one vertical and this force we have. See, like kind of very simple thing we have noted now. This vertical, this force and this force. After this, the angular orientation part also. So whatever angular orientation you are considering, so here it will be like this, here it will be like this, here also 18.4. So that's why, for your understanding purpose, we are trying to just give all those details. So summation of loads along x direction equal to 0, summation of loads along y direction equal to 0. When you just use that thing, we are getting our F4 and F3. You please note F3, it is just like taking 0 dummy number. It is not just like, it is not involving in your strengthening part. So now we have same, in that same line we have same member force only. Next we can treat our joint B. In the joint B there are 4 members. F5, F2, F3, F6. So now what we can do, just like we already noted, F3 part is known, F4 part is known,
And we also noted F2. So those portions, F3, F2, those are no. Only thing F6, F5, you have to note. So F6 also 0 when I use force equilibrium along X and the Y direction equal to 0. It is, we are trying to use local coordinate with respect to this point B. That's why it is XB and YB. So we are arriving F6 equal to 0 Newton and F5 equal to minus 300.317 Newton. In this way, it is just a written. You have to know. Similarly, when you think about your joint E, member 1, 2, 3, 4. 4 members are involving. So now you have to note this. Already F4 portion we have noted from our previous calculation. You have to note this. F4 portion is known. And the F6 also we have noted. Yeah. F6 also we have noted. Only two, F8 and F7 we have to identify. F7 is 0, F8 we are getting 36, 316, 456. We already noted the same lines, the same force should be existing. So now we are trying to see our joint D. In that joint D, obviously it is very, very simple. In that joint D, we have 4 member forces. Like F5, we already noted. Now we have noted F7 also from our previous calculation. And F5 previous calculation we have noted here. Yeah, minus 300.317. After this, we can just like use our force equilibrium with respect to this point D, and we are just arriving our F10 and F9. So you know those details. It is very simple and straightforward. After this, what we are trying to do, we are trying to fix our joint G. In this joint D, we have joint G, 3 members and 2 reactions. So that's why we have to use joint G. In that joint G, we have to think about those reactions and 3 members we should note. 3 members and 2 reactions. So joint G portion we have noted and we have arrived our unknown reactions. Yeah, when you just start from point A directly, we can directly arrive this Hg. We already fixed our Hg from our support reaction calculation. Similarly, we also noted what is our F1. F1 should be 0. So according to this problem, it is very beautiful problem. See all those vertical members, they are taking 0. And one more, this F6 also, I think we got 0 force. Yeah, and we are also getting something like kind of same load along this portion, and we have to note our diagram. Now you can understand. See along this line, whatever load you are just sensing, same load is existing. Here also same load is existing. So now this problem is very simple, straightforward. When you solve these 2 problems, like previous triangle and this cantilever type truss problem, you can thoroughly understand what is method of joint and how we will arrive our unknown member forces. So with this, I will finish our first session. If you have any questions, you can discuss with me. I am waiting for your questions. Madam, any questions?
Participants, do you have any questions? Okay, sir. Then thank you. So we'll meet in 15 minutes, sir. By 3
Yeah, we will meet around 3:20. Is it okay?
3:20. Yeah, 3:20. Okay.
Thank you, ma'am. Thank you very much.
Okay.